We can start the lecture now. Last week we have seen limits and we studied some of the properties. Basically, limit is the behavior of a function as your independent variable approaches to a point. And by behavior, we mean that does the function approaches to a real number L or not? And you approach the point from 2 points, two sides. Either you can approach x of 0 from values which are greater than x of 0, or you can approach values from less than x of 0. So by definition, ordinary limit is a two-sided limit. That's the reason why we try to build an open, symmetrical interval about the point of 0. However, we also need one-sided limits. So today we are going to study one-sided definition and see the properties. I can see my voice here. You hear it right now? Okay, let's continue with one-sided limits. Okay, the notation limit as x approaches the c of f of xl means that the limit of the function is L if x approaches from the left with values less than c, or from the right with values greater than c. Thus, ordinary limits are two-sided by definition, as we said. Now, one-sided limits are denoted like this. Limit as x approaches to c plus, which means values greater than c. F of x gives you the right-hand limit. So, how does your function behave if you approach c from values greater than c? This is called the right-hand limit. Now, if you limit as x approaches c minus, means that you approach c from values less than c, and this gives you the idea about how does your function behave as you approach c values less than c. Therefore, a function may not have an ordinary limit, but have one-sided limit. As you remember, ordinary limit means that the value that function approaches c either from the right or from the left must be the same. And that's the definition of the ordinary limit. The function may not have an ordinary limit, but may have one-sided limits. That's important. We are going to use one-sided too. Okay, let's start with an example. Our function f of x is x divided by the absolute value x. So if you approach 0 from the right-hand side, from those values, the limit is 1. And if you approach from the left-hand side, the limit is minus 1. So actually, the function does not have a limit at x equals 0, but it has one-sided limit. Okay, so you might have f of x as you approach c from the right-hand side might be L. If you approach from the left-hand side, it might be M. If L is not equal to M, you say that the function does not have a limit c, but has one-sided limit. Okay, let's look at this function. Okay, that's the pictorial view. When x is positive, absolute value x is positive, and so it's equal to x, and you have this graph. Now, as you approach 0 on this side, from the right-hand side, it's obvious that the limit is equal to 1. But if you approach x from the negative values, then absolute value of x is minus x. X divided by minus x is minus 1. So here you have left-hand limit as minus 1. So you say that this function does not have a limit at x of 0, but has one-sided limits. This will be important when you start continuing. Let's continue with the examples. Okay, so that's your function f of x. Okay, that's the point C. Function is defined here. So this is the right-hand limit because x approaches C from values greater than C. Okay. Here on this picture, C is here. That's your function. Now it approaches C from the left-hand side, and it has a limit m. Here it has a limit L. That's a pictorial representation of right and left hand limits. Okay, let's look at it. This function. That's a upper semicircle y is equal to square root of 4 minus x squared. This upper semicircle, the picture is like, the drawing is like that. Now, when you approach minus 2 from the right hand side, you have a limit 0. You cannot approach minus 2 from the left hand side because the function is not defined there. So at minus 2, we have a right hand. Similarly, if you look at 2, when you approach 2 from the left hand side, values less than 2, you have a limit. But you cannot approach 2 from the right hand side because the function is not defined. So at minus 2, you have a right limit. At plus 2, you have a left hand limit. Now let's look at this theorem. Actually, we have said what this theorem is saying to us. The function is defined on an open interval containing C. It is not defined at C itself. And f of x has a limit as x approaches C if and only it has left and right hand limits there, and these one-sided limits are equal. So ordinary limit, as we defined last week, that's this one, exists and right hand limits are the same. So that's the basic idea to define left and right limits. If they are the same, you have ordinary limits at that point. If they are not the same, then you only have one-sided limits. You don't have the limit itself. Okay, let's look at this function here. Now that's the piecewise defined function. Between 0 and 1, it's obvious that y is equal to 1 minus x. So when x is 0, you have 1. And as you approach 1, equals 0. And between 1 and 2, it's constant, which is equal to 1. At x equals 2, it's equal to 2. And now between 2 and 3, it behaves like x minus 1. When x is between 2 and 3. So between 3 and 4, 5 minus x at 4, it's 1 over 2. Okay, now let's look at the list of this function at different points. For instance, at x equals 0, does it have a limit? No, it does not have a limit. You can approach 0 on the right-hand side. You cannot approach from the left-hand side. So there is no limit here, but there is a right-hand limit, which is equal to 1, as shown in this table. No limit. Now, let's look at point 1. As you approach point 1, the limit, as you can see from the left-hand side, is equal to 0. So it has a left-hand limit here. If you approach 1 from values greater than 1, as you can see, the limit is 1. So there is no ordinary limit at point 1, but right-hand limit is 1 and left-hand limit is 0. Let's look at 2. As you approach 2 from values less than 2, that's the left side, the limit is 1. As you approach 2 from right-hand side, the limit is 1. So the function has a limit at 2, which is equal to 1, although the function is defined at 2 as 2. Okay? Function value is not the limit, but the limit is 1, the function value is defined. So at 2, you have limit, right-hand limit, and left-hand limit, which are equal, so you have ordinary limit. Let's look at point 3. As you approach 3 from the left-hand side, you get the limit 2. As you approach 3 from the right-hand side, you have the same limit, and the function value is the same. So at point 3, you have a limit, because right and left-hand limits are the same. You have right-hand limit and left-hand limit. Now let's look at the last point. As you approach 4 from the right-hand side, the limit is 1. Left-hand, sorry. Limit is 1, but you cannot approach from the right-hand side because the function is not like that. Okay, so at 4, you only have left-hand limit, which is equal to 1. There is no right-hand limit because there is no ordinary limit. That shows the difference between right-hand limits and limits itself. So you can check right and left-hand limits. If they are equal, you say you have a limit. If they are not equal, you say that there is no ordinary, which is one-sided limits. Let's continue. Okay. That's again, that sort of summarizes our definition. That's the notation we use of the right-hand limit. Now we are going to give a precise definition of one-sided. Now we say that x has right-hand limit L at C, the limit is L, and rightness if for every epsilon greater than 0 there exists alpha greater than 0, f of x minus L is less than epsilon whenever x is in this interval. This does not see. When x is in this interval, this should hold for all x. Okay, so what's the difference between the ordinary limit? When we use ordinary limit, we have a symmetric interval. So we have both and left side. So here we just the right hand limit. Go to see. So for every epsilon, I should find delta. So all x. Now left hand limit is 6. We say as left hand L, And this, as you can see as of x is a. Now, if for every epsilon greater than 0, find alpha greater within this interval. Now, these are the values less or less than p. But for all x, like this must hold, except at c. P may hold, but we don't allow it. But all other values of x in this interval, this must hold. So that's how you find this number alpha greater than 0. So if you can find it, that's the proof that you can write. Okay, let's continue. Pictorial representation of what you mean. When you're given an epsilon greater than 0, because this is L, and you want your function value to be values, L plus 1 and L minus 1. Okay, so we choose delta so that for x greater than c and less than c plus delta, you should give this interval. So when x is in this interval, except c, of course, your function value should lie in these points. That's what, if you can show it, you can say you have a. Okay, that's the left hand limit. Okay, again, you are given an epsilon, and the function value must be between L plus epsilon and L minus epsilon. So you get your interval or you find your delta so that for all x in this interval, this must be whole. The function value must be here. Otherwise, you cannot have left hand limit. Using a square root of 0 and support function 0 hand side. Because on hand side, function is not square root is. Therefore, so that's my epsilon. I want actually should be L is this, that's x minus L less than epsilon. This is a positive number because square root. So I can write as x less than epsilon square. Actual square root of x is epsilon, and take the square and you get x. So you choose delta here, then your and here is epsilon function. That's an example and 0. So for this, because the less than 0. I say as a function sine now when 0 for small value and that there is no real number else so that sine 1 over x minus 0 value for very small value in minus if you can find the delta, which the function will be reaching. Neither from the right hand side nor from the function also. This function does not have a right limit or on. Let's look at this function. Y is equal to sine theta over here theta is in radians. And now as this function is not defined at 0 because sine 0 is 0 and theta is 0. 0 divided by 0 is not a real number. Okay? However, you have a limit. Function is from that here. Find all other values. You can see from the figure approach 1 at 0. Okay, this figure, we are not zero. Okay, there is here 1. What's the say? This is 1. This is 1. And this yellow one is 1. 1. We are going 3 areas here. 1, 4. That's the area of this circle. This area.
Hocam sesiniz çok sık kesiliyor.
What's the problem? Okay. That the areas, not and the last one for TA. There's nothing wrong with my internet connection. Can you hear me now? Can you hear me? Can you hear me now? Okay, I can see my coming out. Uh, you should refresh your pages maybe. Okay, there's this TA. It's the area of this trouble. So let's look at each different area. Now OAP, this triangle, the height is sine, the base is 1, so 1 over 2 sine theta is OAP area. Okay, let's look at this area sector, OPA area sector. That's 1 over 2 r squared theta. When theta is 2 pi, you get pi r squared. So At least that's how you calculate the area sector. So that's 1 over 2 r squared. Now let's look at OTA triangle. Yes, the base is 1. The height is tangent theta. So that's tangent theta. So actually, it's clear from the figure that OPA triangle is less than area of the OPA triangle is less than area of the OPA sector, which is less than the OTA triangle. So these inequality hold, of course, we can just cancel out the 2's here. Now, I can divide everything. Here, r is 1, so r squared is 1, so I didn't write it here. So I can divide everything by sine theta. So we have 1 here, theta over sine theta, and the sine in the tangent cancels out sine theta. You have 1 over cosine theta. So that's the inequality we have here. Now, if you take the reciprocal of everything, cosine theta is less than sine theta over theta, which is less than 1. I just take the reciprocal of everything. So that's the quality we have. Now, as theta approaches to 0, cosine theta approaches to 1, and this is a constant, so it's 1 also. And so the limit as theta approaches to 0 of sine theta over theta is equal to 1. Now, this is a two-sided limit, although this is something written here, but that's a two-sided limit. So we used sandwich theorem to prove that sine theta over theta has a limit 1 at 0. Let's continue. Okay, so that's the theorem proved here. Now, using this result, we can prove other things. For instance, limit as h goes to 0 sine h minus 1 divided by h must be 0. Limit as x approaches to 0 sine 2x over 5 is equal to 2 over 5. Now let's look at first one. We are going to use this theorem or use this result to show that this is true. Okay, for the first one, cosine h minus 1 divided by h is actually minus 2 sine square h over. That's the half angle formula. Okay? So I can write this as I can cast 2 under the h here. So limit as h goes to sine h over 2 divided by h over 2 is the same as this. You can say this theta is h over 2. So that's the same thing. This must be equal to 1, but this is 0. So that's 0. That's the proof that this is 0. Now let's look at the second one. The second one, sine 2x over 5x. As x approaches to 0, we are going to look at this limit. Okay. Now I can multiply the numerator here with 2 over 5 and the denominator 2 over 5, so nothing will change in the limit. It's one of the limit laws. Now I can take 2 over 5 out here. So I have in the denominator 5 cancels with this one, you have 2x. So the limit sine 2x over 2x as x goes to 0, this is equal to 1 multiplied by over 5. So you get the result 2 over 5. So that's the use of this result to prove that these limits are basically true. Okay, let's continue. Okay, now we come to the notion of continuity, which is closely related to limit, the existence of limits. Okay, let's look at the definition first. Let C be a real number that is either an interior point or an endpoint of an interval in the domain of F. So C is interior point or endpoint. Function F is continuous at C if limit as x approaches to C of f of x is equal to f of C. So that's the basic definition of continuity. So when you say that a function is continuous at a point C, the function must be defined as C, because we're not talking about f of C. Plus, its limit as x approaches to C from both sides must be equal to f of C. Okay, so that's for the interior point. C is an interior point. The function f is right continuous at C, or continuous from the right, and we write limit as x approaches to C from the right-hand side of f of x, f of C is f of C. So again here, the function must be defined here, defined at C, when you approach from the right-hand side, right-hand limit must be equal to C. And the function is set to be left continuous at C, or continuous from the left, and we write this. So when you approach C from the left-hand side, you must have a limit plus this limit must be equal to the value of the function, or must be equal to f of C. So that's the basic definition of continuity of a function at a certain point. Now, a function is continuous over an interval at all points, and you say that the function is continuous in this interval. Now let's continue to check check some continuity. This is an example that we have seen. Okay? We look at the limits at point 0, 1, 2, 3, and 4. So let's look at continuity. Now here, when you look at 0, as you approach 0 from the right-hand side, the limit is 1, which is equal to the value of the function. So it's right continuous at this point. This function at 0 is right continuous. Okay, so let's look at point. Now, when you approach 0 from the left-hand side, the limit is 0. The value of the function is 2x. So the function is not continuous at 1. It's discontinuous at 1. Let's look at point 2. Now, as you approach 2 from the left-hand side, you have a limit 1, and as you approach from 2 to 2 from the right-hand side, you have the same limit. The function is not continuous at this point because the function value is 2. So the limit is not equal to the function value. It's not continuous at 2. Now let's look at this point 3. As you approach 3 from the left-hand side, the limit is 2 and the function value is 2. As you approach 3 from the right-hand side, again the limit is 2 and the function value is 2. So the function is continuous at 3. Now if you look at this point 4, as you approach 4 from the left-hand side, the limit is 1. The function value is 1/2. So the function is not continuous. Plus 4, because also they are not approachable on the right hand side because the function is not defined. So when you have a function like this, it's important that you define finance where the function is complete. Now let's look at function defined between A and B. Okay. Now C is an interior point here. It has a limit, and the limit is the function value as you approach from left and right. So there's a limit, and it's equal to the function value. So the function contains all interior points. Okay. Now let's look at endpoints at A. Now there's a right-hand limit. As you approach A from the right-hand side, there's a right-hand limit, and it's equal to the value of the function. So it's right continuous at A. Now if you look at B, as you approach from the left-hand side, it's left continuous because the limit exists and it's equal to the value of the function. So you say here in this case, the function is continuous over this interval. Although you have left-hand limit here, right-hand limit here, since these are the endpoints, the function is not defined out of points. You say the function is continuous in this closed interval. If it's right continuous on the left-hand point and left continuous on the right point. So that's how you end up with continuity of a function closed interval. The interior points, you look at the ordinary limits. Ordinary limits must exist and must be equal to the value of the function at that point. But at the endpoints, you look at one-sided limits. If they exist, or if the function is left or right continuous at points, then you say the function is continuous. Same is true for this function that we have seen before. Y is equal to 4 minus x squared. Now the function is defined between minus 2 and plus 2. And we know that as you minus 2 from the right hand side, the limit is 0 and the function value is 0. So it's right continuous at minus 2. And as you approach 2 from the left hand side, it's left continuous at 2. And for all interior points, it's continuous. So the function is continuous over its domain. And its domain is closed interval minus 2 and plus 2. Okay, there's another function here. This is called a unit step function actually. Now for x is less than 0, its value is 0. If x greater than or equal to 0, and its value is 1. So when you approach 0, you approach 0 from the right and left hand side, but it's not continuous at 0 because it has jump discontinuity at this point 0. So the function has jump discontinuity at 0, but it's continuous everywhere else. So the continuity test is this. A function f of x is continuous at a point x equals to c. It can only have these following conditions. F of c exists, so the function must be defined at c. Limit as x approaches c of f of x exists, and limit as x approaches c of x is f of c. So the limit must be equal to function value. Of course, the endpoints you look at right hand and left hand. But at the interior points, that's how you test. Let's look at this function. That's the greatest integer function we have seen before. Okay, it's right continuous at every integer, but not left continuous. As you can see, between 0 and 1, okay, greatest integer is greatest integer, which is less than or equal x, so that's 0 here in this interval. As you approach 0 from the right hand side, you have a limit 0 and the function value is 0, and so there is right continuity here. But when you approach left 1 from the left hand side, the limit is 0, the function value is 1, so it's not that right continuous here. It's not continuous here. Okay? It's not left continuous, it's only right continuous. Okay, so the greatest integer function is right continuous, not left continuous. Let's look at function y is equal to plus 1. That's continuous throughout its domain. As you can see, x plus 1 here is not defined at x0, so 0 is not in its domain. It's discontinuous at x0 because it's not defined. However, it's continuous throughout its domain. Okay, this type of discontinuity is removable. So if we change the definition of function as 1 at x0, then that's we remove this discontinuity, and this function is then continuous throughout the domain. If you put 2 here, again the function is not continuous at x0 because the limit is equal to 1 and the function value is not equal to 1. Okay, let me just show that here. Okay, y is equal to f of x is continuous here. Here y is equal to f of x not defined at 0, it's not continuous here because one of the requirements of continuous function must be defined this way. And now when you look at 2, here the function has a limit 1 at 0, but the function value is 2, so the limit is not equal function value. And that's why we say that it's discontinuous at 0. So there's a jump discontinuity here, and that's the basic difference. So in these 3 types or 2 types here, there's a removable discontinuity. I can instead of 1 here, and this function will continue throughout this domain. Okay, let's go back to the previous figure, previous page. This function is not continuous at x equal to 0 because it has discontinuity. And y is equal to sine 2x pi over x has oscillating discontinuity at 0. These are shown here. So 1 over x squared, and as x approaches to 0, either from the left or from the right, the function grows. There's no limit. If you give me a number as a limit of this, to find x values so that this function is greater than the number you give. So you have infinite discontinuity here, which is not removable, of course. And here, if you give me a number, I can find x so that it's not, it does not stay in any interval that I'm giving. Who's playing with this pointer? Okay, let's continue. Okay, let's look at this function. Y is equal to 1 over x. That's the graph of the function. As you can see, you don't have continuity at 0 because you approach 0 from the right-hand side, the function grows too much. If you approach from the left-hand side, function becomes small too much. So there is no limit at 0. However, this function is continuous throughout the domain because its domain does not include 0. Its domain is minus infinity 0, union 0, infinity. These are open intervals. It's continuous throughout its domain, but it's discontinuous at 0. Okay, now let's look at summarize sort of properties of continuous function. These are almost obvious. Sum of difference of two functions. So if you're given a function which is continuous at C, F and G are functions like this, then their algebraic sum endings are continuous. If you multiply with a number k, multiplication of two functions are continuous. The ratio of two functions are continuous. Of course, here p of c must not be 0. If n is a positive integer, that's continuous. And root, if f exists, it's continuous. That is negative, root may not exist. So continuity rules are like limits. Continuity is based on the limit. So the rules are similar. Now let's look at composition of continuous functions. If f is continuous at c and g is continuous at f of c, and the composition gf is continuous. This is sort of obvious too. So f is continuous at c and g is continuous at f of c, composite function is continuous. See, that's a pictorial representation. So you have f continuous at c, and this is f of c, and f of c is in the domain of g. So g continues at f of c, then the composite function continues at c. Now the polynomials and rational functions are continuous throughout their domains. This is also true for absolute value function. Y is equal to x. Absolute value. Sine x and cosine x are continuous everywhere because the domain is all real numbers. All 6 trigonometric functions come throughout their domains. For instance, y is y tangent x. That's not defined at minus pi over 2, plus pi over 2, pi over 3, pi over 2, pi over 5, pi over 5, etc., etc. But these are not in the domain anyhow. It is not finite points, so they are continuous throughout their domains. Okay, let's consider a composite function. Y is equal to x squared minus x minus 6. Now let f of x be this, g of x be square root of. So y is equal to g of f of x is this. Now x plus 2, I can factorize this x plus 2 and x minus 2. So what is the domain of this function? Of course, this minus into minus 2. Minus 2 side is closed. You can set this minus 2 to be 0, so the 0 square root of 0 is 0. And 3 infinity, and 3 is closed here. X is 2, that's 0, so everything is 0. So this is continuous throughout the domain because uh, f of x is continuous everywhere. Its domain is all real numbers. It's continuous everywhere. G of x is g of x is square root of. Its domain is 0 infinity. G of f of x, uh, g of x is defined except negative values. G of f of x, this is all positive. These are defined everywhere, but g of x is defined for all positive values, so that's how you get the domain. Here, when you're in the interval, that's always positive. X is negative here, and x is negative here, negative, that is negative, positive. Same is true here. Okay, so that's a typical example of the continuity of positive functions. Okay, let's give a break now for 8 minutes, and we'll convene at 10 o'clock.
يا عيني